to Science Pub, where the top minds at Oregon State University share their passions in work and research with our community members. This is Nathan Moses, Assistant Director for Events and Engagement at OSU-Cascades, and I thank you for joining us tonight. We're going to be joined in short order by Dr. Bryson Robertson, who will present on wave energy, role in decarbonizing our energy system, and why Oregon. But first, let's get to some announcements. First up is a reminder for the OSU Connections portal. This new application is live and open to all alumni. This is your new online professional and social network tool to connect with others in Beaver Nation. Share advice and stories, find jobs, volunteer, and much, much more. Check us out at osukconnections.org. And then just a final reminder as we get to the end of our Science Pub season, we've got a couple upcoming Science Pubs that will be up here. Those of you that missed Ryan Reese's event, you'll want to check out that one on our YouTube channel from last week or for 2 weeks ago. And this is going to be home of all of our recorded live streams for Science Pub. Coming up, we're going to have a presentation on the OSU Prototype Development Lab on May 25th and the Gut Ecosystems and Relevance to Human Health presentation on June 7th. Stay on the lookout for those events coming up through your emails. All right, so next up, again, Mentimeter. You hear me say this all the time, but make sure everybody is crystal clear on how we do audience feedback for Science Pub. You're going to go to Mentimeter, www.menti.com, or you can download the Mentimeter app on your smart device. You're going to plug in tonight event code 31716107, which is at the bottom of your screens tonight. You can also take a snazzy photo of that QR code on screen right now and get that directly on your mobile device. You all can ask questions directly through that portal as soon as Bryson starts his presentation, or as he gets done with the presentation this evening. So feel free, chime in. More questions we get, the better dialogue we have for the Q&A. So look forward to all those responses for tonight. Okay, the other thing is too, those of you that are joining us that have YouTube accounts, we do pull questions from the YouTube chat. So if you want to do that, that is also another opportunity if you do not want to use the Mentimeter app tonight. All right, well, we're going to get right into the core of our program tonight, and I'm going to introduce to you all Dr. Bryson Robertson. So Dr. Robertson began his career earning his bachelor's degree in mechanical engineering from the University of Victoria, his master's degree in civil engineering from Queen's University, and his PhD in coast engineering from the University of Guelph. Dr. Robertson's research focuses on detailed wave, tidal, and offshore wind energy resource assessments, optimizing energy harvesting technologies, and numerically integrating marine power into the electrical grid at a variety of scale and opportunities. In complementary research, Dr. Robertson has also looked at the future of our global energy systems, the nexus of technology, policy, economics, and society on the decarbonization of electrical systems, and the public trust requirements to transition power systems. Bryson was recently included in the CNBC piece around the Packwave project, and tonight he generously gives us his time here at Science Pub. So Bryson, thanks again so much. Welcome, and the floor is yours, my friend.
Thanks for the generous introduction. I'm delighted to be here. I'm really excited to go through this presentation. I assume folks can see my slides. Are we good to go? I'm gonna take nothing as a yes. There we go. Okay, so I'm here on behalf of the Pacific Marine Energy Center. So the Pacific Marine Energy Center is a collaboration between Oregon State University, University of Washington, and the University of Alaska Fairbanks, where we all work together to advance the marine energy industry. So my talk tonight is around wave energy and its role in decarbonizing our energy system, and why Oregon. So first things first, I think it bears repeating that the past does not represent the future. And I think in the context that we live right now, I think this is incredibly important. Number one, we can't look backwards in our ecological system to understand what it's going to look like in the future. The climate has changed, the climate is changing, so we can't look backwards to trends to understand where we're going. Additionally, we have new tools that we can use. So we can't look to the past to say, how did we solve that problem? And how do we solve it again with those same tools? Because now we have new tools, new problems. Additionally, we have new knowledge. You know, in the past, we didn't understand that what the impact we were having on the climate and our energy system was having on the climate. We now know that. So we can't look back to the way people have done in the past because the world has changed. So how do we move forward into the future? So based upon the latest research from OCRI, the Oregon Climate Change Research Institute on OSU campus, this is what they're predicting for Oregon in the year 2050. We're looking at increases of temperature by about 5 degrees, increased rainfall events in the winter, and longer, drier summers. Less snow and only at higher elevations. Forest fires are both going to increase in burnt area and frequency. We're looking at more flooding and increasing ocean acidity. So when we look to the past, the future is changing, the future is new, and we're having an impact on it. So what are we going to do about it? So given that climate change is happening and it's predominantly driven by emissions, where are those emissions coming? If we're going to try and focus in on where we can have the greatest impact, if we're going to try and decarbonize and we're going to start to look towards a more sustainable future, where do we need to focus our attention? So these are the latest stats from both the EPA, the Environmental Protection Agency, and the Energy Information Agency about where are our emissions coming from. So on the left, we see a pie chart, a snapshot of where we've seen the US emissions coming from in 2019, which is some of the latest numbers. And you're seeing predominantly driven by transportation, then electricity, then industry. And on the right-hand side, we see how that's changed over time. You know, when I gave this presentation a couple of years ago, and we had 2017, 2016 numbers, the electric power industry still dominated where our emissions were coming from. But that's changed over the last number of years. And normally that is a great win. I shouldn't say normally that's a great win, it is. But let's not confuse reducing emissions with increased renewables. What's driving this change right now is we're shuttering coal plants and we're starting up natural gas plants. So where we see that decrease in the electric power industry, that's purely from the switch from coal to natural gas. It's not the increase of renewables that's driving that change. If we look at our other sectors, transportation, industry, agriculture, emissions are pretty static. If anything, maybe they're slightly trending upwards. So we need to really change and identify where we're going to focus our attention to change this trend and hopefully reduce the worst impacts of climate change. So sitting here in the US, where does our power come from? So we're about 40% natural gas, give or take, 20% coal, 20% nuclear, 7% hydro, and then 13% are our other renewables. And that's wind, that's solar, that's geothermal, that's biomass, that's a slew of different technologies, but still we're predominantly fossil fuel driven. So where are we going? So this is an old quote, but I think it is always a good one and it gives you good context. The most plausible way to reduce our global CO2 emissions is to increase the role of very low carbon technologies in electricity generation, and then to increase the use of electricity in transportation and heating. So step one, let's increase the amount of renewable electricity that we generate. And then let's use that additional electricity to substitute for fossil fuels. And let's focus on transportation and heating. There are some of our most emissions intensive areas. So let's really focus in on those two sectors. So what does that look like as we look out globally? Where do we see this sort of change happening? And this is a recent plot by the International Energy Agency, where they're looking at how do we see the world transitioning under current economic practices, under current projections of pricing, all those sorts of nuances. The red line across the screen indicates where we are now in 2021. So you'll see between now and 2050, we're really seeing massive increases in solar PV and offshore and onshore wind, which is fantastic. Really great penetrations of renewables coming into the system, really allowing us to maybe get to more than half of our generation is coming from wind and solar. But we're not really seeing dramatic reductions in gas fire, nuclear staying on there, hydropower staying on there. And we still even have some coal and oil out to 2050. So while we are making great progress to this, we are starting to see a heavy dependence on two renewables. We're seeing a heavy dependence on wind and solar, which is great. And we really need to see them take off. But what does the impact of a renewable future dependent purely upon two renewables look like? And how do they, if we don't start to introduce more renewables into that pool of tools or resources that we can use, we're really never going to get at those bits at the bottom, that gas, that oil, and that coal fire, which we really need to push out of the system. So going back to that quote a couple slides ago, where we need to, number one, we need to increase the amount of renewable electricity. So what impact does that have? I'm scrolling around. We need to really increase our electricity. So we got two plots here. On the left, we've got a Canadian scenario, and on the right, we've got a US scenario. So focusing on the right-hand side for right now, the goal here is to look at the total energy consumption. We're at around 4,000 terawatt hours a year currently, and this is a bit dated, but since 2018 and with COVID, we haven't changed dramatically. But in order, as we go forward and we look to electrification, we're seeing anywhere from sort of a 20 to a 60% increase in the total amount of electricity we need to generate. And this is with predictions of us getting better at everything we do. We still need to make 60% more power than we do right now. So our energy system needs to get 60% larger. We may have taken 100 years to get to this stage, but in the next 30 years, we need to build an additional 60% of that whole system. So massive build-up needs to happen. And on the left-hand side, we have a Canadian scenario where they're saying, well, what do we need to do in Canada to do this? Let's look at all the technologies we have in our bucket to electrify. And you see, it may be up to sort of a 4 times increase in power. It all depends on where we predict in terms of costs, efficiencies, build out, batteries, a whole slew of things. And you'll see I've crossed off a number of lines there in the middle, because I'm sort of saying, these aren't decarbonization technologies. These might get us to a goal of electrifying, but they're not going to electrify in a renewable fashion. They're going to just create more emissions. So what do we end up with in most of these? We get solar, wind, get a bit of biomass. That's a long discussion. And then we have other. We have this giant generic other. What are our other renewables that we're going to rely upon? Is it fairy dust? Is it unicorns? What are we going to rely on to fill that gap between what wind and solar do for us? So as a system operator, so when electricity is different from other commodities in the fact that when you generate it, someone must use it. So that same instant that your wind turbines spinning or solar panels generating power or your gas turbines making power, you need a user on the other end to utilize it at the exact same instant. You can't store it on the grid. Yes, we're getting better at batteries. Hydropower provides us a huge amount of storage, but from a fundamental, the electricity system works different from other commodities in the fact that your supply and your demand have to be time synchronized so that as soon as you produce it, you have a user. If you produce it and there's no user, the whole grid goes unstable. So there are a number across the world in all the jurisdictions, they're system operators. So people whose only job is to make sure that they have enough supply to meet the demand. People demand power and they don't really care where it comes from. We turn on our lights, we use electricity. So they have to manage the supply side to match that. So on the left-hand side, we've got a plot of wind energy in BPA, so in the Northwest. And on our x-axis, we have 24 hours. And on the lower panel is over a month. So we're going to quickly look at what wind generation looks like in the Pacific Northwest over a month. And you can see how that plot's moving in the 24-hour window. It's going all over the show. If you come down to the bottom, you're seeing, wow, you're seeing these massive fluctuations in when that wind's available. So this is what we'll call a variable resource. This is something where it varies between 0 and 4,000 in this picture. Massively variable, and we don't quite know when it's going to come on or when it's going to turn off, but we have to manage this grid in order to accept this wind. And when we've got small amounts of power, it's great. When the wind comes up, we'll turn off some natural gas or we'll turn down a hydro dam. We'll sort of buffer it. We'll manage those. On the right-hand side, we have solar in California. And this is where I'm sort of trying to difference between variable and intermittent. Solar is what we'd call intermittent. And what you're seeing here is, well, we know solar doesn't work at night. So there's 12 hours of the day where we know it's 0. But in that other 12-hour period of the day when the sun is shining, we're going from sort of 0 to 9,000 in this picture very quickly. And that's sort of intermittent. So it ramps up really quickly and then hits that plateau and then ramps down really quickly. So renewables are intermittent. They are variable. It's just an inherent characteristic of these sort of renewable energy flows. They're not sort of turn it on, turn it off, like a diesel system or a natural gas plant or a coal plant. These are systems that, you know, we need to extract from power when they're available. And given this paradigm where we need to have a demand on the same side, it becomes a game as we start to get to higher and higher penetrations of renewables. So what does this mean? So this plot, I'm going to take a sec to try and explain this here. So across our x-axis, we have a 24-hour period. And this was from January 11th last year. So we've got a 24-hour period across the bottom. On the left-hand side of the plot, we have the megawatts. So let's think about, that's just generation. That's how much electricity we're making. The magnitude doesn't really matter. That's just what electricity are we making. And our orange and green line, orange are non-renewables, so fossil fuels. Green are renewables. And the first thing you see is at night time in California, the non-renewables, so our fossil fuels, generally make all our power. And the renewables are pretty close to zero. And then the sun comes up and that renewables, that green bar jumps up and we get all this good renewable power. We turn off our natural gas plants and it sort of evens out during that middle of the day period. And then come the evening, solar goes offline, it goes way down towards zero, and we turn up all our gas plants again to make sure we meet everyone's demands when they get home and they want to turn on the power and cook and heat their homes and everything. So that's just the dynamic. But what happens is the purple line here is the price. So how does the price of that power change during that period? And you see, as the renewables come on, as our solar comes on, as our green solar comes up, the price drops right out. And if you're looking carefully, you'll notice that it actually goes below zero. So at this period of the day, California is paying us in the Northwest to turn off our hydro dams, to not generate power. They will pay us to use their solar power. So this is the difference. I'm trying to illustrate the difference between cost and value. While solar is getting incredibly cheap and we need to see more of it in the grid, it doesn't mean it's valuable. And value is very much determined upon the time of day and who needs power. In California now, they have too much solar at certain times of the year and certain times of the day. So they're paying people in the Northwest to use their power. So as we get, and this is only going to increase, as we get more and more solar in the system and it all comes on at the same time of the day, unless we have a lot of people who start using power at that time of the day, it's no longer valuable and the price will be negative. So there is risk when we start to develop a renewable future that's dependent on something that goes to zero and wind, which is incredibly variable. The other thing that we need to be aware of as we move to this renewable future, which we need to do, and I'm a huge advocate, but we need to understand all the impacts. Land. So in the top figure here, some latest numbers, I think from the EIA, the Energy Information Agency, around the acres of land needed to generate the same amount of power. And coal, natural gas, nuclear all sit around 12. You know, when we go up to solar, we see about a 4 times increase. We're going to need about 4 times more land to generate the same amount. If we go out to wind, we're sort of 6 times more land we're going to need to generate that same megawatt hour. Hydro, again, it's way up, but all of these are slightly, they offer different things, but the goal is here just to show that you need a lot more. If we look down at the bottom, now this is a little bit harder to understand, but on the right-hand pane, we just have the total amount of electricity generation that we can, this is sort of capacity. So how many solar panels, how many wind farms do we have out there? And as we move to an era beyond natural gas, when we stop relying on natural gas to drive our decarbonization, and we really start to rely on those wind and solar that we've seen in all of these plots for all over the world, what happens? And on the left-hand side, we have this sort of land area impacted. And, you know, we can debate whether it starts at 800 or it starts at 2000, and we can debate whether it goes to 7,000 or 5,000. But fundamentally, we're going to need a lot more land. And last time I checked, no one was giving land away, and no one was trying to reduce our natural parks or get farmers off their fields or reduce the size of our cities. We are a lot of people and we need land. So if you have a resource that doesn't use land, there's a very high percentage chance that that's going to become incredibly valuable as we move forward. So again, coming back to this plot, a number of things. This plot, and a lot of this planning relies on two things, wind and solar. But it also keeps natural gas, and it keeps oil and keeps gas fire. And that's not good enough if we're going to reduce our impacts on the climate. We need to get after those fossil fuels, and we need to push them out of the system. And that's one of the reasons why wave energy helps. We really start to diversify. We can push out these hard to reach areas. There's a whole slew of advantages. So here's some latest numbers of what do our marine energy resources. So sort of switching gears again. I've talked about some of the issues, some of the challenges, and now I'm going to try and talk about why does marine energy play a role. So here we got a map of the US regions, the exclusive economic zones of some of the US regions. I'm just going to focus on the light blue, which is the wave energy portion. And you see all these different regions. You know, Alaska has a great marine energy resource, great wave energy resource when it's not frozen in the winter, if we're up in the Bering Sea. Hawaii has a great resource, but fundamentally most of the reliable wave energy resource is based on the West Coast. And within that, most of it is in Oregon and Washington. So we have the sort of, if we classify it as the most energetic waves, this is where it's based in the US. So this is why a lot of the activity and the resources spent and the academic research and the companies are often based in Oregon, is because we have this fundamental, very active resource. And we also have a very supportive climate. We've got a state who's putting their hands up and saying, yes, we will support this. Universities putting their hands up and saying we'll support this. And we see this important as we go towards 100% renewable futures. So I'm not going to spend too much time on this, but we can sort of come back to tidal. It's a different type of marine resource, but we'll come back to it later on in the question period. So I'm going to focus here on wave technologies. So we talked about the resource. And that's sort of like, I guess, how big is your dam, or how much coal do you have in the ground? But then you need an energy technology to extract it. And wave is different from solar panels, where all of us know what a solar panel is. And with the wind energy companies have sort of coalesced around, we're going to have 3 blades, and we're going to have it horizontal, and we're going to have the 3 blades spin around the horizontal axis, and we'll build our whole industry around that. Wave energy is not there. We have a whole slew of different technology archetypes. So on the far left, we have what's called an attenuator, where we have a hinged rigid body, where as the waves pass by and this hinge moves, we extract energy from this hinge and the relative motion as the wave passes. There are technologies like Resolute Marine Energy in the middle left, based in Boston, which is a flat type system, where as the wave passes, it pushes the device back and forth, which might go to push a hydraulic ram and desalinate water or create electric power. Columbia Power in the middle right has a technology which utilizes the relative motion of the waves as they pass, and the device is spinning, or the vertical motion as it goes up and down. On the far right, we have a technology where you have what's known as a vertical axis pendulum. So a pendulum that spins around. You design your device so the hull is excited by the waves and wants to move like this, and then you get a big pendulum that starts to spin. So it's kind of like a flywheel plus a wave energy device moved together. So there's a whole slew of technologies that are all looking to harness waves. So again, why Oregon? So again, here's another plot. I'm going to focus just on the blue lines for right now. This is a 2-year period. Blue line is telling us, when do we need electricity? When do we demand electricity in Oregon? And the 2 things you'll notice are in the winter time, so December, January, February, is when our demand is the highest. That's when it's cold, and it's dark. So we're heating our homes, we're lighting our homes, we're cooking more. In the summertime, like July and August, our demand sort of drops by half. Maybe not half, maybe a third. It drops way off. We use a lot less power in the summer. So again, that's a period of time where we don't need a lot of electricity. We're not looking for a lot of electricity at that time of year because we don't need it. We need it in the winter time. So the orange line is mapping the wave energy resource over that exact same time period. And we'll see it spikes at the exact same time. So when our demand for power is the greatest is when the wave energy resource at our shores is the largest. If we plotted solar on this, it would have the exact opposite sort of trajectory. There would be very little correlation. It would be, as you know, when the summer comes and we get lots of our solar panels, lots of power, solar power, is when we demand the power the least. So we'd make too much. Not we'd make too much, we can only build so much. The other thing is predictability. So I showed those plots of the variable and intermittent of the wind and the solar. Wave energy has this great advantage that we can predict it with really high accuracy a long way out into the future. It's almost like one way to think about it is the whole Pacific is sort of our watershed for wave energy. If there is a storm anywhere in the Pacific, the waves generated from that storm will end up on our coastline somewhere. And once waves are created, they can travel vast distances without using a lot of power. And so we kind of know exactly when they're going to show up on the beach. So if we know a storm happened in New Zealand 2 days ago, we can tell you in 3 days it's going to arrive in Oregon. So we have this great predictability. So when we're trying to manage the system, the electrical system, we've got the right tools. We've got more knowledge, and knowledge is power, and knowledge is value. The other thing to keep in mind here is under our current system, most of our electricity or our renewables are built out in the Central Valley because the wind blows and the sun shines. You know, let's be honest, it's cloudy on the coast and the wind's intermittent. If you go out to the Central Valley, sun shines a lot more and the wind blows a lot more. It's great resources. But we need to get those resources back to the urban centers where people live. So we need to, when you're comparing wind and solar against something else, we need to compare what's the cost of building it, then what's the cost of building the transmission line, and then what's the cost of losing the efficiency losses along that line, and what happens when that line drops or it goes down. So here are two maps of just the instantaneous price of power at a number of different locations. These are both California maps because their data is just a little more accessible. And you'll see, say on the right-hand side, where these red dots indicate that the price of power is somewhere above $150 a megawatt hour. A blue dot means it's negative. And what's happened here is the demand in the city is so high that they can't push enough electricity through the power lines to get into that city, so the price goes up because the supply is not there. So if you had a renewable resource that could help decarbonize, that was more predictable, and you could deploy it right near major cities, that's a highly valuable resource. When we talk a little bit smaller scale, and I won't spend too much time on this, a lot of our remote communities, Alaska, Canada, our islands, they suffer from energy poverty. They rely upon a shipping expensive, polluting diesel to them or oil so they can generate power. The cost of power for 7, 10, 12 times what we pay, and they can't create economic growth. They can't stay in their communities and be viable. They migrate to the city centers, and these sort of communities die off because the price of power is so high. And there's huge social inequity that happens with that. So if we look at the right-hand map, which is Alaska, and I think they did a great job of painting all the non-renewables blue and all the renewables red, but that's just me. But you'll see that most of these bars are showing oil-fired, gas and oil. A lot of Alaska is found by oil, and we need to find ways to power these, because a lot of these coastal communities have great renewable wave resources. We just need to harness them. So we've talked a lot about, what's the global setting? Why are we doing this? Where are the technologies? But what's Oregon State's role in this? What's Oregon State? So the Pacific Marine Energy Center, like I said, is a group of academics, a group of universities, R1 universities, who are looking to responsibly advance marine energy by expanding scientific understanding, engaging stakeholders, and educating the workforce of tomorrow. So one of the great things about being affiliated with such fantastic universities is we have this amazing plethora of experts in every space. So if we want someone who's an expert in wave forecasting or maritime robotics or sediment transport, we can go and tap that person on the shoulder and say, hey, can we use your expertise and your knowledge to help solve problems and issues for the marine energy sector to move forward? Do you know about energy policy or the impact of crabs and fisheries? Can we tap you on the shoulder to come join the club and help us out? So we like to think of ourselves as both a mile wide and a mile deep. So these are all different activities that we have ongoing. within PMEC at the 3 universities. At OSU, our program has been running since the early 2000s, so getting on 2 decades here. We've really ramped up in the last decade, though, with about 130 million in funding for R&D and the development of Packwave, which we'll chat about in a second. We've spun out a number of different companies, so Columbia Power, Aquaharmonics, 3Wave, 3M, all spun out of OSU, graduates and IP coming from the university. As a university, we've deployed a lot of technologies. We've graduated a lot of highly skilled and well-paid workforce, which are out in the national labs, supply chain, a number of different places. And quite frankly, I think we've tested more devices than any other place in the country. Well, I can say that with some certainty, we've tested more. And I would say we're up in the top sort of 5 or 10 in the world in terms of testing and helping move this industry forward. So what are those facilities? What do they do for us? So on the far left, we have WESURF, the Wallace Energy Systems and Renewables Facility, where we do all our electrical connections. So here we can play with the campus electrical grid. We can put some solar in, we can put some wind in, we can put wave in, some battery storage, and we can just start to understand what are the dynamics of the system. In the middle left, we have the OH Hinsdale Wave Research Laboratory, which is where we don't need to be too modest. It's an absolutely fantastic facility where we've tested a lot of the US manufacturers, developers' devices. We build small scale devices, we deploy them at Hinsdale, and we get to learn a lot about them as a proof of concept. On the right-hand side, we have Packwave, which is the new big project on the horizon, which is a grid-connected 20 megawatt facility, which will be the first fully energetic wave site out of Europe for companies to come and test their technologies. So previously and historically, companies have sort of developed, got so far along the line, and then they want to go and do fully energetic testing and they have to leave the US. They'll go to Europe. But now we're building Packwave so they can come and test here, and so that the world can come here and test in Oregon and in the US. So for folks who don't aware of Packwave, it's about 7 nautical miles offshore. We've got a map. I'll focus on the map on the right. We've got Newport. If you go down the coast, the red box here is where we'll be connecting to land. We're running a cable 7 nautical miles offshore to these berths, which is just at this stage really a cabled connection, which then we'll be able to run that power back through the cable, back into the local community grid, and be able to power local loads. But like I said, this will be the first pre-permitted testing location. This isn't a commercial enterprise. This is for companies to come and test, develop, get stakeholder and funder support, and then move elsewhere and test and build at scale. So how do people on the coast feel about this? Like I said, we try and take a very broad view of marine energy and the value proposition. We need to understand the stakeholder perspectives. So here we have a map. This was a survey of all our West Coast states from Alaska to California, including British Columbia and Canada. How do people feel about all these different resources? So, you know, wave is incredibly, people feel like we should continue to increase the utilization of wave. Of all those, if we add up, increase and keep the same, wave is actually the most popular in terms of our renewable resources development. So that's great news for us. That sort of gives us, we have sort of social buy-in from our coastal stakeholders. Additionally, if we look across the political spectrum and trying to understand where we're going to see our support, you know, here again, we've got that same mapping. And, you know, I've highlighted wave here because if we look at the spread between our different sort of political values, wave consistently is well supported. People see it as an opportunity for us to grow domestic technologies, deploy domestic technologies, increase, bring other companies to our country, as well as to utilize our resources here to decarbonize our system. So broad support, which is a really fantastic thing for us. So just to give folks perspective, this isn't just study. This is a video of the ocean energy device that was built in Vigor Shipyards up in Portland a couple of years ago, just prior to COVID sort of setting up. It gives you a scale. This isn't just studies. This isn't just numerical academics playing in their world. This is an industry that is developing. We are building technologies, we are testing technologies, and we will get to scale. Part of it is it takes time to build these. It takes tests and time to access the ocean, but we are making great progress along the way to developing this industry. So just gives you a sense of scale. This is a big one. This is the biggest one that's being built. So they're not all this size, but this is just the scale and the manufacturing jobs and a lot of the other things that come along with the development of this industry. But there's other things we can learn. So sort of taking a step back. If we look on the left-hand side, we've got a plot of the map of the Pacific Ocean. And I'm a nerd for maps. I'll look at maps all day long. But what strikes me about this one is a couple things. One, if we look at the globe from this perspective, pretty much half of it, or pretty much the whole side, is just ocean. Massive amounts of ocean. And two, it's just painted this blue, like this blasé blue. Like we look at the land base, we've got all this detail in the mountains and this, and then we've just got blue for the ocean. Quite frankly, that's because we don't know that much about a lot of this. But if we think about that, we know there's waves everywhere in that ocean. We know there's a resource there to extract and to harness. And if we can make power everywhere in the ocean, we can start to understand it. We can map it. We can explore it. We can track it. And fundamentally, historically, we've been held back because we didn't have enough power and availability to different parts of the ocean. And then if we look at the right-hand side, maybe we should take a page out of some of our other competitors' books. The solar energy industry started with the calculator. It started with that little calculator. They're like, before we try and dominate a sector and put solar panels on every roof, we're going to just try and power a calculator. So we're doing a lot of effort to say, can we do the same with wave energy? Should we try and power an ocean buoy? Should we try and power a sensor? Should we power an underwater vehicle? What other opportunities can we sort of create commercial enterprises quicker that will then pave the way towards large-scale utility power? So a lot of this, a lot of this is sort of being branded as powering the blue economy. So how can wave energy sustainably power this new blue economy, which is dominating so many economic discussions? Because as we go to power our blue economy, let's do it sustainably. Let's learn from the past and let's do it in a more sustainable, resilient fashion. So can we power underwater vehicles? Can we create desalinated water? Because water, quite frankly, is a more valuable resource to a lot of people than some electrons. Can we power our isolated communities? Instead of when there's a disaster in the world and a tsunami comes through or a hurricane blows up, instead of shipping in diesel and shipping in bottles of water, can we ship in a crate of a wave energy converter that gets deployed offshore that produces fresh water in a sustainable fashion? So there's a whole slew of different activities, and we have students engaged in all of these activities. We're trying to produce wave energy converters where underwater vehicles can come and dock. So they'll charge up, they'll download all their data, they'll get more power, and they'll be able to fly off and take new measurements and map the seafloor and bring new knowledge while that data gets streamed back to scientists. And it's just because we had power on the site from the wave energy converter. We're trying to make water, there's a whole slew of activities here. So when we say the past does not represent the future, most people inherently say, well, here's the challenge. But I always like to spin that around and say, here's the opportunity. Here's what we can do. Here's the new tools we have. So finally, just some resources, some things to sort of make this real, to further explore. For university students, sign up to join the OSU Marine Energy Collegiate Competition team. There's a sign up link there. I can distribute the slides. Play RoboWave, which is our little video game here that the students created where you can get power up with power by taking your submarine up to the wave energy converter and then go and collect shells. On the PMAC website, there's a whole slew of educational resources from K-12 lessons plan, coloring books, even a little project where grad students develop a small wave energy converter you can make at home and just use it in a bathtub and make some power. Social media, all those bits and pieces. So just a great slew of resources for folks to use there. And with that, I'm going to leave it there, but hopefully we have some good questions.
Well, we do indeed. And I think you might have set the record for the most number of questions submitted during the presentation. So we definitely have an attentive audience tonight. I just got to point out first before we get to Q&A, I had not considered it before, but, I think, we're talking about waves. And I get that. but powering the flight industry with fairy dust. I think that enough people aren't tapping into that yet, man. I think that's something that we're overlooking. But Bryson, thank you, man. This is really good. I mean, really, really interesting. And I will say, the other night I had a really long night working on some paperwork, and I came across the RoboWave deal, and I was like, I got to try this out, and it was fantastic. So I think the cool thing about this all being on YouTube and being able to go back and rewind is you all will be able to get those links on the site, and or I should say on our recording. So definitely check that out. But yeah, let's get right to it, because there are a number coming in, and I think they are kind of all over the place, and I love that. Couple different things that folks are putting in. So one of them is, you talked a little bit about different types of renewables.
Yep.
And specifically when we're talking about waves, I love that grid of like kind of showing like the kind of the US, North America, where some of that wave energy could potentially come from.
I can pop back up there.
Yeah. That was perfect. And I think one of these questions is relying on this. River energy harvesting, it seems like there may be some more predictability in that, though I think based on your graphic, I think the potential is lower than coastal. Can you talk a little bit about maybe the uses for river energy harvesting and how that kind of plays in this whole piece, even though I know, again,
No,
the coastal wave is your deal.
Yeah, no. So we rivers and tidals are 100% within our purview at the Pacific Marine Energy Center, and we do a lot of work on that. And yes, incredibly consistent, reliable resources where you can put a turbine in. And the two of the big successes in the last year was we put a river turbine in Igiugig, Alaska, to power a remote community there in a sustainable fashion. And as well, just in New York, they just put Verdant Power Systems just put 3 turbines on the bottom of the East River to power a part of New York. The problems with rivers is we just don't have that many. And you do have impacts on the environment because you've got to wait for this enclosed environment where the water velocity gets up high enough that you can generate power sustainably. And that works well. And one of the issues with rivers, and everything's got its issues, and we just overcome them, is that particularly in very energetic things, is you have a lot of debris floating down the river. So if you're up in Alaska and you've got a 200-foot Douglas fir floating down the river, it's a bit of a bummer when it hits your device. So there's pros and cons, and you find the right technology for the right place. And I think that's the sort of overarching story for all of this, is you've got to find the right technology for your right location to meet your demand. There isn't a silver bullet in this renewables game. There isn't one. We need all of them.
That's perfect. And actually, I'm going to stay right there on that same track. So a couple of the questions come down around impacts in kind of the oceanic coastal environment with some of these technologies.
Yeah.
One of which was the example that you'd used up in Alaska. The comment is a lot of garbage lands on Alaskan beaches. Presume this will produce entanglement with wave energy devices, even though I will say it looks like some of the devices that were created, it's less about turbine and more about movement. So is there sort of an impact on some of the, I guess, the coastal garbage, if you will, on any of the devices you guys are working with?
Yeah, I think, sort of before we get to the garbage specific one, I think we need to all acknowledge that everything we do has an impact. Absolutely everything. There's no free lunches in the world here. So, as we move from fossil fuels, we're going to stop, fracking, and we're going to stop doing that. But we're going to have an impact somewhere else. There's no impact in sort of solution. But of those, we spend a lot of time and effort as a community globally. So this is definitely one of the benefits. Is as a community around the world, everyone is very focused on responsibly advancing marine energy. And you'll notice that in our title, it's not responsibly advancing marine energy industry or marine energy technologies. It's responsibly involving that whole sector, doing it in a responsible manner. So we do spend a lot of time trying to understand the environmental impacts. So moving to the sort of plastics and marine pollution things, yeah, I would almost flip that and say that's an opportunity, because as we create these smaller scale devices, perhaps what we actually need to do is utilize that energy to drive them around and capture plastics. So rather than saying it's going to get impacted, let's go, we got power on this thing now, let's go take it somewhere and let's go and collect it. There's probably going to be some tangle issues, but these are big devices. Again, water bottle is not going to have a huge impact on it. A big fishing net, sure. Ghost nets, sure. But as long as we do it in a responsible manner, such that we can turn it off, we can get to it, we can track it. I think we've got new tools at our disposal to be able to sort of mitigate some of those impacts.
Great response. One thing on this too is looking at some of the native populations on the coastline. You talked about the project being about 7 miles off the coast.
Yeah.
What about anything like migrating whale populations or any sort of an impact on the environment of kind of those ebbs and flows of the species that are coming through that environment? Any sort of an impact you guys have registered at this point with that, or?
No, that's a great one. So I guess first, and this is before my time, but that location, so that 7 miles out location, was not identified by OSU or a wave energy company. That was actually identified by the local fishing community. So the FINE group, the fishermen involved in natural energy based in Newport, and I believe they've got representation up and down the coast. They actually identified that site. They said, this is the place where you're gonna have the least impact on our sort of commercial activity. So that's where it was ended up. And in terms of impact on whales and things like that, we're really at this stage, all of the permitting is required that if there is impact, we can remove. And we're looking at what's happened in Europe, what's happened in Hawaii. So they've got a test site in Hawaii, smaller scale, less energetic. But again, Hawaii's got a lot of whales. So we're looking at what their environmental monitoring program is. Have they had any impact? Have they seen things change? What is it? But at this stage, there has been very limited change. It's sort of undiscernible on a lot of things. But we're keeping that very front and center in terms of making sure that we do not create negative change.
Well, I mean, just even looking at the location it's at, I looked at moving a wind turbine. I would imagine, you guys are dealing with some huge things in the water, but it's also in the water. So I imagine there's probably some opportunities that maybe relocation is a little bit easier in the marine environment, even though you're talking about equipment that is, I mean, that was impressive. That piece you showed at the shipyard, that is amazing to see that scale.
Yeah, no, yeah, there are relocations, but we also, we've been harvesting and utilizing things from ocean for a long time. We as a population on land, we harvest the ocean all the time. So it's not this sort of barren wasteland where no one goes out there. There are fishermen out there every day utilizing it for their livelihood. So we've got to make sure we mitigate all those concerns and we find sustainable solutions.
Awesome. One of the individual, you talked a little bit about wind. Anything in specific about benefits of offshore wind? Is that more consistent? Is that something that maybe more emphasis should be put on?
So yeah, offshore wind is coming. There's no debating that offshore wind's coming. So one of the reasons we're doing offshore wind as a sort of global entity is one, it comes down to partially that land issue is, it's not just the immediate land that people view, but it's view sheds. People don't want to see wind turbines. They want them far away. We're running out of land on land to generate terrestrially. So in Europe, what they've done is they've moved out into the North Sea. Now the North Sea is shallow, so you can mount your turbine to the seafloor, and then you can put somewhat generic sort of wind turbines on top of it. We can do that on the East Coast. So we've seen the East Coast, the Block Islands and the Vineyard Winds and all the sort of massive amounts of offshore wind we're seeing penetrate on the East Coast, and sort of increasingly, they're going to be that same technology, mounted to the seafloor, a turbine up, because they have a large continental shelf. Now, when you come to the West Coast, we don't have that large continental shelf. You go to Hawaii, you don't have that continental shelf. It drops off. So we have to go floating. So we're going to design our devices to go out and we can moor them. So it opens up the area. Like now we can go in a large amount of places. The other advantages to going offshore is your wind resource is a lot more consistent. So we are way more efficient offshore than we are on land because we don't have mountains and bushes and trees and bridges and disturbing the wind flow. It's a much more consistent, smooth, clean wind flow. So you're way more efficient. And then quite frankly, you can build it bigger. One of the issues with building terrestrial land turbines is we can't get the parts from the factory to the site because our roads bend too much. So if you're building a blade that's sort of 50 meters, you can't go around every corner without like cutting off someone's roof or hitting a bridge. So transporting them from the factory to the facility is actually one of the biggest constraints. But when you build it offshore, you build it in a port, you put it on a ship, and you drive your ship out there. And now you can build it much bigger. And one of the benefits of wind is as you increase that diameter, it's not like you're just getting slightly more, you're getting it to the cubes. You're just getting, every time you go wider, you get cubic amounts more power. So it's pretty powerful.
Yeah, I guess that makes total sense. I'm so glad somebody asked that. That's great. Another one coming up. Let's see, man, I can't even keep up tonight, guys. Good job, everybody. Let's see here. Okay, so one of the thing is acoustic impacts. What sort of acoustic impacts are we looking at in some of these technologies, and is there research that's been done on the impact of that noise on transient species?
100%. So yeah, there's a huge amount of acoustic research going on. You know, if we look at most of the deployments thus far, we have to surround the whole site with acoustic sensors. Some of our first sensors powered by wave energy devices were acoustic sensors, purely for this reason, to understand what the acoustics are. So with Packwave, which is the permitted test site of Newport, we're actually like at the scale where we're pushing acoustic technology into new places to make it better, so that we can get a very robust understanding of the soundscape out there, and we can start to identify where do technologies fit in it, and for a number of reasons, both from environmental and species risk, but also it's in a powerful way for us to understand maybe how the technology is doing. Because let's remember, these are offshore, we don't get to see them. It's not like we can stand at the bottom and look at the wind turbine. It's out there, and sometimes the acoustics can give us a lot of knowledge about what's happening. Is the device working properly, or do we need to go and get it? There are things like that. So acoustics are incredibly important. And like I said, we're developing a whole slew of new technologies. We've got experts from around the world who've identified in the acoustic space, who have identified this is the next thing to go and look at. But all the research thus far, very little impact. So we'll see. We're not saying it's not there, because we'll see once we get more devices in the water.
Yeah, great. Yeah, I think one of the most fascinating things about tonight, and I had never really considered this before, again, this is not my expertise, clearly, but looking at cost versus value, because I think we are pumped this whole piece that solar energy is so much more cost effective and we're going to save so much money. But looking at it like you're talking about, that it requires the integration of multiple types of resources to be able to affect the overall system. Mm-hmm. Clearly, I understand why then that's not used in a lot of commercials, especially for like residential solar and things like that. Like, it makes more sense now. But in looking at this, I guess, what would you say trajectory-wise, what some of the most expensive green premiums are on the industry? And then where do you see, like, maybe in the next 5 to 10 years, because of emerging technology, do you see any adjustments and cost?
Oh, yeah, you know, there's a portion of the energy system sort of analysts who are almost saying that electricity is going to be free in the future. There's going to be so much of it that it's going to be free. But what you're going to pay for is sort of your access to it. So thinking of it almost like how you buy your internet now. You buy like a total amount of data, but then you also buy a speed. And maybe that's where the energy industry goes, is that you buy a certain amount of electricity, but then you also buy how much do you want, like instantaneously. And that's where now that, you know, solar is getting so cheap. No one ever saw this coming. It's getting incredibly cheap, but it's driving battery technology, which is fantastic. And, you know, I think in a lot of parts of the world, the combination of solar and batteries will get us a long way, because then you just need to build a battery to last you through the night, which is a very small amount of total energy to get you through the night. But if you're not going to build a battery to get you through the winter, like you're not going to, that's the issue. And that's where, you know, people are looking at hydrogen. Maybe that's where hydrogen steps in and allows us to use this almost free solar power to generate hydrogen, and then we can use a fuel cell to make electricity. Now that sort of chain of events has huge amounts of efficiency losses and costs. So by the time at the end, you're not getting that much, but they're getting better. But if we can develop wave where it's produced at the instant that there's a demand for it, it's a much cleaner transaction. So where do I see changes? battery technology is definitely going to change the game. I'm still hopeful that, at this stage, hydrogen is going to play a big role in our future, because particularly when we get to transportation, we're not going to build electric airplanes very well, but we can build electric hydrogen airplanes, and that sort of heavy duty, high energy intensity sort of parts of transportation. I think we're going to need a sort of a chemical fuel to allow us to do that. And let's make that. We can synthesize a renewable fuel. That's not hard to do. We can do that, but we need lots of electricity.
Yeah, the battery conversation, and again, this is just speculation this question's coming from, is do you think that it's going to be kind of like a homeowner system where it's going to be like individual batteries per home or per business or per industrial park, and that's kind of how it's going to be set up, or do you see the technology going in a different way?
Well, this is a great example of where we see technology, and I'm an engineer, so I'm going to bash myself. Technology and engineers versus like what society wants, because if everyone has a battery in their house, it's actually a much less efficient system. So in the world, if we modeled the US right now and we gave everyone a battery for free, what ends up happening is we actually burn more coal. Is because the battery is inefficient. By the time you take the power in, you lose power. And when you pull it back out, you lose power. So as a country, we now have to produce more power to account for this flow, for the efficiency losses. So we end up burning more. So as you deploy batteries, you need to couple it with producing more and more renewable electricity. Because if we just build batteries, it's not good. It's like if you're living in a state which is dominated by coal electricity, buying an electric car is not a good thing. Why would you burn coal to make electricity, to transport an electrical cable, to power a car, when you could just put fuel in your car and burn it? It's just maybe more efficient. So there's what do they call horses for courses? There's sort of solutions in specific places.
Oh, good. Great answer. Let's see here. And it looks like we've got, yeah, and again, question just around energy storage going to be an option. So, I mean, I think, to your point, it seems like there's just so much evolution with battery types, and, who knows what 10 years down the road is gonna give us.
Yeah. And I think batteries are incredible, and what Tesla's doing and what so many companies are doing is phenomenal. But I think there's a sense of scale here that I think often gets lost. The amount of power we use within the US, within the world, is astronomical. And the amount of batteries you need to build to buffer that much power is massive. It's unbelievable. Like, we did a study just looking at solar and batteries to power a house in this is when I was in Canada, just for a house in Victoria. Victoria's quite a sunny little place for a West Coast town. And you pretty much had to fill your basement with batteries, and then you had to buy an acreage to get solar panels. The scale's hard, and we have long winters, which are dark, and it's tough. The scale's just so big when we get to utility scale power. I think there are a lot of really exciting opportunities where batteries are going to be incredibly valuable to us. Maybe not in sort of decarbonization, but in terms of reducing costs. So yeah, there's a lot of nuances around that. But I think storage is definitely part of the solution, but it's not a silver bullet. It's not a ubiquitous solution. The scale's just hard, and I think just like everything, to make batteries don't just appear. We've got to go mine down mountains in other parts of the world to go and get the resources to build batteries. So there's impact.
Right. Which, again, all too often we don't think about. We think about that. It's like, oh, great, this new technology, but sometimes where those resources are coming from can be convoluted and complex.
Yeah.
The question that came up about storage in general: what is the potential for some sort of a system for creating a giant reservoir that you pump water into when there's excess electricity, and then let it go to turbines when the need increases? So I guess maybe this is talking about kind of like those evening winter type situations.
Yeah. No, so that's what we'd call just pumped storage. So, despite all these advances in batteries and how much press it gets, the most efficient way for us to do this still is to pump water up a hill. So we use our electricity, we pump water up a hill, wait for wait for us till it needs some electricity, and we let it roll back down the hill. So a couple things there. One, again, getting to the social question, try and build a large scale dam these days. Like you are not getting public confidence, social license. You're not getting access to that land to dam a valley, to build a storage facility that's big enough. So that's one thing. And then again, the scale of it is amazing. So I forget what the numbers are, but I think for a state like Oregon, and I might be off by 2 times here, but the biggest pump storage facilities in Bath County, and I think just to do Oregon and our storage requirements, we'd need like 30 times the biggest pump storage facility that there is right now. The scale is just so big that we need to drown valleys. Now, the goal is to not create new facilities, but just use hydro dams that we have more efficiently. So allow, within those hydro dams that we have, allow us to pump water back up into them. And that's not always allowed by regulations, because again, we've got to go back to the environmental impact. There's huge impacts on salmon and fish in the rivers, and how do we maintain all these different ecosystems. So it's a lot of people say that's probably the most regulated place in the world, is hydro dams and rivers.
Okay, excellent. All right, thank you. Everybody, thank you so much for the questions. I do want to hit on one more thing, and actually, if we can go back and show the slide for the resources page that you ended with. One of, like, I love highlighting the students. Actually, the last resource.
Oh, the last one. I got you.
The one that has the. You're gonna get to it before
the
I
RoboWave.
Explain it. The RoboWave. I think one of the coolest aspects of Science Pub is when you guys get to talk about kind of the student integration and the work that you're doing. And one program that I was not very familiar with was a recent competition that does happen annually that we've got some partners with, and you talked about it. It's the Marine Energy Collegiate Competition, and I believe that they won some awards recently, and I actually watched the video. I think it's about a 58 minute video of the submissions for the contest, which I thought were amazing. Can you talk a little bit about the MEC and kind of, I guess, what they do, how to get involved, and a little bit about it?
Yeah, so this, I gotta say, is a completely student-led activity. I'm sort of the mentor, but let's use that term very broadly. They do all the work, yeah. And this video game came out. RoboWave came out of it. So the Marine Energy Collegiate Competition is a Department of Energy sponsored activity to say, let's try and get collegiate teams to start to work on challenges in the marine energy industry and how can they develop solutions. So the competition has it's multidisciplinary. You have to come up with a business plan. You have to develop a wave energy converter, and you have to test it. Well, the testing part is an optional third party. But so at OSU, we had a team of about 15 students, and they were civil engineers, mechanical engineers, electrical engineers, environmental engineers, oceanographers, energy policy folks, business school folks. So pretty much for most of the schools across campus, we had representation of at grad and undergrad level, more undergrad because it's focused on undergrad. And they brought together a pitch. They spent 8 months working on this project, and they won 2 awards. So one they won was the Outreach Award. They were incredible. So they were up in Portland at what was the event? Noches de Ciencias, where they distributed 50 kits of these sort of small wave energy converters that you could sort of make in a bathtub, and they gave them out to students, and they did presentations, and they ran through this. They also won an award on the build and test, where again, the university, through some of the flexible funding, where they were able to access Hinsdale, the wave lab that I was talking about. And that's the biggest non-military wave lab in the US. And the students got to spend a week in there testing their devices, running waves, and just, that is an incredible resource. No one gets to just access that. You know, when I was in Canada, we had to travel 8 hours by airplane and spend $50,000 to access that. But here, the students could just go and use it. And so I definitely encourage people to sign up. I'd love to have pictures of all the students on here, because really they did all the work. They created this video game. They made the coloring book. They did all this. So I encourage you all to go look at that, because they did an incredible job.
Oh, that's awesome. And yeah, no, I had to give a little bit of shout out to them because I was just so impressed with the work they did. And then again, all these resources, everybody in the audience, definitely check them out because, not only did you probably learn a whole lot tonight, you're going to continue your learning journey through some of these pieces. So I appreciate the ability to have access to this and you talking about it. So I really, really appreciate it. Well, that is fantastic. Well, tonight, again, we all learned a lot. I have some reading to do because, again, I grew up in the Midwest. So, when you want to become a marine biologist because of Shark Week, that's about my only access. This has opened up a whole new world for me. So Bryson, I really, really appreciate that. For everyone in the audience, again, I would love so much to thank you again for joining us in this collaborative Bend and Corvallis campuses science pub. Massive thank you to Bryson and all his time and efforts in putting the presentation together tonight and participating with the audience Q&A, which, as I told you when we did our prep, this was going to be one of the more fun parts of the presentation. So really appreciate everybody with that tonight. Additionally, big thank you to OMSI and Terra Magazine as kind of partners with this for our science pubs. And again, our wonderful team at Connect Central Oregon. Shout out to Brent tonight for running our production studio to make this live on YouTube. This concludes our science pub for Monday, May 10th. 2021. Tell a friend about your experiences tonight. Shoot us topic ideas if you'd like to see in the future, and we will be starting to put those lists together for next year. So definitely let us know at events@osucascades.edu for those topics you'd like to see for next year. We look forward to seeing you in the future, and we look forward to you joining us out there next time. Have a great evening, everybody, and thank you again.